You can point the most powerful telescope ever built at a patch of plain, empty-looking sky and expect to find faint, ordinary galaxies. That is roughly what astronomers expected when the James Webb Space Telescope first opened its eyes 1 million miles from Earth. Instead, the images came back speckled with tiny red points of light. They were small, they were red, and they were almost everywhere. We now call them the little red dots, and for a few years they were one of the strangest puzzles in all of astronomy. They sit so far away that their light is nearly as old as the universe itself. They looked too bright, and there seemed to be far too many of them, far too early. Tonight, we're going to follow that puzzle gently, from the first surprise all the way to the answer that finally arrived. So what, exactly, are they? Picture a single machine, the size of a tennis court when its sunshield is unfurled, floating in the cold dark 1 million miles from Earth. That is the James Webb Space Telescope. It does not circle our planet the way the older Hubble Space Telescope does. Instead, it rests at a quiet point in space called the second Lagrange point, a place where the pull of the Earth and the Sun balance, so the telescope can hover there with very little effort. From that perch, far beyond the Moon, it keeps its back to the Sun, the Earth, and the Moon all at once, shielded from their light and heat. That shielding matters more than it might sound. The James Webb Space Telescope was built to see infrared light, which is light just a little too red for human eyes to notice. We feel infrared as warmth. The trouble is that warm things glow in infrared, including the telescope itself. So Webb is kept bitterly cold, colder than 200 degrees below zero on the Celsius scale, so that its own faint heat does not drown out the faint heat of the distant universe. Why chase infrared light at all? Because the universe is expanding, and that expansion stretches light as it travels. Light that left a young galaxy as ordinary visible colour arrives here, billions of years later, stretched into the infrared. To see the first galaxies, you must see in the infrared. The older Hubble Space Telescope, for all its beauty, could only peer a little way into that range. Webb was made to go further. Its main mirror is the key. It spans more than 6 meters across, far wider than Hubble's, and it is not a single sheet of glass. It is built from 18 smaller mirror segments, each one a 6-sided tile coated in a microscopically thin layer of pure gold. Gold reflects infrared light beautifully. Folded up for launch, the mirror looked like a golden honeycomb. Once in space, the 18 segments were nudged into near-perfect alignment, so they act as one great eye. The James Webb Space Telescope launched on the 25th of December in the year 2021. It then spent a month travelling out to its distant post, slowly unfolding as it went. Its first full-colour images were shared with the world the following summer, and almost at once it began doing what it was built to do, which is to gather the oldest, faintest light in the cosmos. That faint light is the whole point. Because light travels at a fixed speed, looking far away is the same as looking back in time. When Webb captures light that has travelled for 13 billion years, it is not seeing those galaxies as they are now. It is seeing them as they were, long ago, when the universe was young. The telescope is, in a real sense, a time machine made of gold and cold metal. Astronomers expected this time machine to reveal faint, ordinary early galaxies, dim smudges from the dawn of everything. They pointed it at small patches of sky and waited for the light to trickle in. What came back was both that and something else entirely. Scattered through those deep images were small, sharp, oddly red points of light that no one had quite predicted. To understand why those little points caused such a stir, we first need to look closely at what astronomers actually saw. In image after image, almost everywhere they turned the telescope. The surprise did not arrive all at once. It crept in, image by image. When the James Webb Space Telescope began taking its first deep pictures of the sky, in the second half of the year 2022, astronomers did what they always do. They opened the images and started counting galaxies, and there, again and again, were tiny red points of light, sharp as pinpricks, sitting among the larger smudges of more familiar galaxies. At first, a stray red dot here or there is nothing remarkable. The sky is full of odd specks, but these were different in two ways. They were extremely small on the sky, so small they looked almost like single points rather than spread out galaxies, and they were a deep, distinct red, unlike most of their neighbours. The more astronomers looked, the more of them they found. They turned up in one survey, then another, then another. One of the early hunting grounds was a survey called the Cosmic Evolution Early Release Science Program, known by the short name CEERS. It studied a strip of sky that has been examined many times before by many telescopes. Then came other surveys with their own names, like the James Webb Advanced Deep Extragalactic Survey, called JADES, and the Next Generation Deep Extragalactic Exploratory Public Survey, called NGDEEP. Wherever these surveys looked deeply enough, the little red dots appeared. That ubiquity is what unsettled people. As the astrophysicist Dale Kocevski of Colby College has put it, these objects seemed to be in nearly every image the telescope took. They were not a rare freak. They were a feature of the early universe, common and widespread that had simply been invisible until now. And that is the heart of why they were missed for so long. The older Hubble Space Telescope, looking mostly in visible light, could not catch them. Their light had been stretched too far into the infrared by the expansion of the universe. They had been hiding in plain sight, beyond Hubble's reach, waiting for a telescope tuned to exactly the right colours. Webb was that telescope. Think of it like walking the same dark beach every night for years with a dim flashlight, seeing only the nearest stones. Then one night you bring a far brighter lamp, and the whole beach reveals small red shells you never knew were there, scattered all around your feet. They had been there the entire time, you simply could not see them. The dots also behaved oddly when astronomers measured their distance. Almost all of them sat at enormous distances, which meant their light was enormously old. They clustered in a narrow slice of cosmic history, the universe's early childhood, and then, curiously, they seemed to thin out and vanish in later eras. They were a feature of one specific time, not of all time. So astronomers now had a genuine mystery on their hands. Here was a whole population of objects, abundant, compact, red, and very old, that had never been seen clearly before. They did not match the faint, ordinary galaxies that had been expected. They looked like something with its own story, a story written into the early universe and then largely closed. Before anyone could ask what they were, the objects needed a name, something plain enough to use in conversation. The name that stuck was as simple and honest as the objects themselves looked, and like all good plain names, it told you exactly what you were looking at, while quietly hiding just how strange the thing really was. Astronomers love a grand name. The sky is full of them, full of catalogue numbers and Greek letters and long technical labels. So it is almost funny that this whole population of mysterious objects ended up with one of the plainest names in modern astronomy. They're called simply little red dots, 3 short words, and each word does real work. Start with the last word, dots. On the sky, these objects look like points. A normal galaxy, even a distant one, usually appears slightly spread out, a small fuzzy patch. You can often see that it has some size and shape. The little red dots do not show that. They look compact, unresolved, like a single dot of light rather than a sprawling island of stars. That compactness is one of their defining traits, and it turns out to be a real clue, not just an effect of distance. Now the middle word, red. These objects glow with a strong, distinctive redness. In the language of telescopes, they are bright at the longer, redder wavelengths and faint at the shorter, bluer ones. To the instruments aboard the James Webb Space Telescope, they stand out clearly against bluer neighbours. That red colour is not decoration. It is a signature, and much of this whole story is the slow effort to read what that red colour is actually telling us. And the first word, little. They appear tiny on the sky, yes, but the word carries a second meaning that took longer to earn. As we'll see, the engines hidden inside these dots turned out to be far smaller than astronomers first feared, so the name, chosen casually, ended up being more honest than anyone expected. Put the words together, and you have the plain truth of the first look. They are little, they are red, they are points of light, like dots, little red dots. Scientists often shorten it further to the initials L, R, D, and simply say LRDs in conversation. But the full plain name is the one worth holding on to, because it keeps us close to what was actually seen. It helps to know how many we're talking about. By the year 2025, astronomers had gathered a careful sample of these objects numbering in the hundreds. One widely cited count reached 341 of them, identified across several deep surveys. That is not a handful of oddities. That is a genuine population, large enough to study as a group, to compare one against another, and to ask what they have in common. And they do have a great deal in common. They share that compact point-like look. They share the strong red colour. They share, as we'll find, a particular pattern in their light and a particular slice of cosmic time when they lived. When a few objects look alike, it might be chance. When hundreds look alike, you are no longer looking at accidents. You're looking at a kind of thing, a class, with its own rules and its own origin. That is what makes the plain name so fitting. It does not pretend to explain, it simply describes little red dots. The explaining would come later, and it would take years and dozens of teams and some genuinely surprising physics. But to even begin explaining them, astronomers needed to answer a more basic question first. Just how far away are these dots, and therefore how far back in time are we looking? The answer comes from one of the most elegant tricks in all of astronomy, a trick hidden in the colour of light itself. Here is a fact that sounds almost too convenient to be true. By carefully measuring the colour of an object's light, astronomers can tell how far away it is, and therefore how long ago its light began its journey. The tool that makes this possible is called redshift, and it is worth understanding plainly, because nearly everything about the little red dots rests on it. Start with a sound you already know. When an ambulance races toward you, its siren sounds high and tight. As it passes and speeds away, the pitch drops and stretches lower. The siren itself never changes. What changes is that the sound waves get squashed as the ambulance approaches and stretched as it leaves. Light behaves in a similar way. When a source of light moves away from you, its light waves are stretched, and stretching light makes it redder. That stretching is the redshift. Now add the great fact of our universe, discovered nearly a century ago by the astronomer Edwin Hubble, after whom the older space telescope is named. The universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they recede. So the farther the light has travelled, the more the expanding space has stretched it, and the redder it has become by the time it reaches us. Distance and redshift go hand in hand. Astronomers measure this stretch with great precision using an instrument called a spectrograph. Aboard the James Webb Space Telescope, the main one is called the Near-Infrared Spectrograph, or NIR-SPEC. It spreads an object's light out into its component colours, the way a prism spreads sunlight into a rainbow. Within that spread, certain elements, like hydrogen, leave sharp marks at very specific colours. We know exactly what colours those marks should sit at, so when we find them shifted toward the red, we can measure exactly how far they have moved, and that gives us the redshift with real accuracy. The redshift is usually written as a number that astronomers call Z. A higher Z means more stretching, more distance, and older light. The little red dots sit at high values of Z, often between 4 and 11. That may sound abstract, so let us turn it into time. A redshift around 7 means we are seeing light that left its source when the universe was only about 700 million years old, out of its current age of nearly 14 billion years. The universe was a small child, and these dots were shining in its nursery. This is why redshift matters so much. It is not only a measure of distance, it is a clock. By reading the stretch in the light, you read how deep into the past you're looking. Each little red dot is a frozen postcard from a specific moment in cosmic history, and the redshift tells you when that postcard was sent. Tie it to something you can hold. Imagine receiving a letter that took 13 years to arrive. You would know it described a 13-year-old version of the writer. Now stretch that to 13 billion years. The little red dots are letters that old. Their light describes objects as they were when the cosmos itself was newly formed, and everything we say about them is a statement about that distant dawn. So we know these dots are far, and we know they are ancient. The natural next question is sharper. What was the universe actually like in that early era, the era these dots seem to call home? To picture them properly, we have to picture the strange young cosmos around them. Let us set the scene by stepping all the way back. The universe began, as far as we can tell, about 13.8 billion years ago, in the event we call the Big Bang. For its first few 100 million years, it was a very different place from the star-filled sky you see tonight. There were no galaxies yet, no spiral arms, no bright clusters. There was mostly hydrogen and helium gas, spread thin and slowly clumping under gravity in the cold and the dark. Astronomers call this stretch the cosmic dark ages, and then the slow lighting up that followed is called cosmic dawn. The little red dots live right at that dawn. When astronomers measured the ages of the dots across their large samples, a clear pattern emerged. The dots begin to appear in great numbers around 600 million years after the Big Bang. Their numbers swell and reach a peak a little later, around 900 million years after the beginning. Then, as the universe ages further, they begin to fade from the record. Hold those numbers against the life of the universe to feel them. Nearly 14 billion years have passed since the beginning. 600 million years is therefore only the first few percent of all cosmic time. If you imagine the whole history of the universe squeezed into a single year, the little red dots would all flourish within the first 2 or 3 weeks of January, and then quietly bow out. They are creatures of the very early morning. That timing is part of what made them so startling. The early universe was supposed to be simple and sparse. Gas had only just begun to gather. The first stars and the first small galaxies were only starting to form. You would not expect that delicate, half-built cosmos to be sprinkled with hundreds of bright, compact red objects all blazing away. Yet there they were, common and confident, in an era that should have been quiet. And then comes the second strange part of their timing. They do not last. As astronomers look at later and later epochs, the little red dots grow rarer, and by roughly 1.5 billion years after the Big Bang, they have largely disappeared. We see no clear examples nearby in the present-day universe of the same kind of object. Whatever they were a phase, a chapter, that the universe opened early and then closed. This is genuinely unusual. Many kinds of cosmic objects, like ordinary galaxies or normal stars, exist across vast stretches of time. You can find them young and old, near and far. The little red dots break that habit. They are tied to one specific window of cosmic history, present at the dawn and then gone. That alone hinted that they were not just ordinary galaxies seen far away. They were something that belonged to the early universe in particular. If you find this faint window into the first morning of the cosmos as quietly moving as I do, you might consider subscribing, so you can wander through more of these slow nighttime journeys whenever you like. So the little red dots gave astronomers a specific time-stamped puzzle. Here is a kind of object, abundant and bright, born at cosmic dawn and gone soon after. The next step was to look harder at the two plain facts in their name, their redness and their smallness, and ask what those features could be quietly telling us about the things themselves. Two simple facts sit at the centre of these objects, and both were visible from the very first images. They are red, and they are small. Before any deep theory, astronomers ask the obvious question. In nature, what makes a distant object look red, and what makes it look small? The answers narrow the possibilities and they shape everything that follows. Take the redness first. There are a few honest ways for an object to look red to a telescope. One is distance itself. As we have seen, the expansion of the universe stretches light toward the red, so very distant objects naturally look redder. But the little red dots are redder than distance alone can explain. Something about the objects themselves is adding red on top of the stretch. A second way to look red is to be full of dust. Cosmic dust, which is really just fine grains of carbon and silicate, scatters and absorbs blue light far more easily than red light. So light passing through a dusty cloud comes out reddened, in exactly the way a sunset turns red as its light slips through the thick, dusty air near the horizon. A dusty galaxy looks red for the same reason your evening sky does. A third way to look red is to be glowing with cooler, longer wavelength light, the way a dying ember glows red rather than white. If an object's light is dominated by emission at the redder end, it will look red regardless of dust. As we'll see much later, this third path turns out to matter enormously. But in the early days, dust was the leading suspect, because dust is common and dust reddens. Now take the smallness, which is the more demanding clue. The little red dots look like points, unresolved, even to the sharp eye of the James Webb Space Telescope. That tells you the light is coming from a very compact region. A normal galaxy spreads its light across thousands of light years, and even at great distance it shows some width. These dots do not. Their light is concentrated into a tiny space. That compactness is a strong constraint. It means whatever is producing the light is packed tightly. You cannot spread the glow of a great sprawling galaxy into a single point. So either the object is genuinely small, or its light is dominated by a small, intensely bright core that outshines everything around it. Both ideas would return again and again as the mystery unfolded. Put the two clues together and a tension appears. The objects are bright, which usually suggests a lot of light, which usually suggests a lot of stuff, but they are also tiny, which means all that brightness is crammed into a very small space. Bright and compact is a difficult combination. In nature, the most extreme way to be both very bright and very small is to have a feeding black hole at the centre, but that is getting ahead of the story. Astronomers measured the apparent sizes carefully and found that many little red dots are extraordinarily compact, with their light coming from a region perhaps a few hundred light years across or even less. For a source so luminous, that is a remarkably small box to fit it all into. So from just two plain facts, redness and smallness, astronomers already had a shape for the puzzle. Something compact, something luminous, something reddened. The trouble was not that there were no explanations. The trouble was that the most natural explanation, when you did the arithmetic, seemed to demand far too much, far too early. And that arithmetic is where the real alarm began. Now we reach the knot at the heart of the early mystery. It is a problem of brightness, and it comes down to a simple chain of reasoning that, followed honestly, led somewhere uncomfortable. The chain begins with a fair assumption, and ends with a number that seemed impossible. Here is the assumption. When astronomers first saw the little red dots, the most natural guess was that their light came from stars, the way the light of an ordinary galaxy does. Galaxies shine because they are full of stars. So if a little red dot is bright, the straightforward reading is that it must contain a great many stars to produce all that light. Now follow the chain. To make these dots as bright as they appear, at the distances measured, you would need an enormous mass of stars packed into that tiny compact space. When astronomers ran the numbers, treating the light as starlight, some of the dots seem to require as much mass in stars as a large modern galaxy holds, like our own Milky Way, or even more. And they would need to have built all of that within the first few 100 million years after the Big Bang. That is the impossible part. Building a galaxy's worth of stars takes time. Gas has to gather, cool, and collapse. Stars have to form, generation after generation. Our best understanding of how the universe grows The framework astronomers simply call the Standard Model of Cosmology sets a kind of speed limit on how fast structure can assemble in the early universe. The little red dots, red as great balls of stars, seem to break that speed limit. They looked too massive, too soon. To feel the strangeness, imagine visiting a town founded only a week ago and finding it already holds skyscrapers, full streets, and a population of millions. You would not conclude that towns grow that fast. You would conclude that you had misunderstood something about what you were seeing. That was exactly the position astronomers found themselves in. And remember, this was not one strange object. It was a whole abundant population, hundreds of them, all apparently too bright and too massive for their age. A single oddity can be dismissed as a fluke or a measurement error. An entire common population cannot. If the reading was right, then the early universe was somehow assembling huge amounts of mass at a pace that our theories said should be impossible. There was also the matter of just how many there were. In the early universe, around the time the dots peaked, they appeared to make up a startling fraction of all the bright, unusual sources astronomers could find. By some accounts, around 1 in 5 of a particular class of bright early sources were little red dots. That is not a rounding error. That is a major component of the early cosmic population. So the brightness problem was really a problem of accounting. Take the light at face value as starlight, and the books did not balance. There was too much mass, in too little space, far too early, and in far too many places. Either our understanding of how the universe grows was badly wrong, or our reading of the dot's light was badly wrong. That fork in the road is where the real drama entered. For a time, some headlines suggested the more dramatic option, that these dots might mean our entire picture of cosmic history was broken. To understand why that fear took hold, and why it was eventually calmed, we need to look closely at what breaking cosmology would actually have meant. For a while, the little red dots carried a heavy phrase around with them. People spoke of them as objects that might break cosmology, or break the universe. It is a dramatic phrase, and it deserves a plain and calm explanation, because what was really being said is more interesting and less frightening than the words suggest. Cosmology is the study of the universe as a whole, its history and its growth. Over the last century, astronomers built up a remarkably successful picture of that history, the Standard Model of Cosmology. It describes a universe that began hot and dense, expanded and cooled, and slowly grew structure as gravity gathered gas into stars, stars into galaxies, and galaxies into clusters. This model has passed test after test. It predicts the faint afterglow of the Big Bang. It predicts the proportions of hydrogen and helium. It predicts how galaxies cluster across the sky. A central feature of this model is patience. Structure grows gradually. Small things form first, then merge and build into larger things over billions of years. The model sets expectations for how much mass should exist, in what forms, at each age of the universe. Those expectations had matched the older observations from the Hubble Space Telescope and from ground-based telescopes quite well. So when the little red dots appeared to hold enormous masses of stars far earlier than the patient model allowed, it looked, on the surface, like a contradiction. If you truly had galaxy-sized masses of stars in place a few 100 million years after the Big Bang, in great numbers, then something in that careful, well-tested model would have to give. That is what breaking cosmology meant. It meant that a foundational theory, confirmed many times, might be failing its newest test. It is worth pausing to feel how serious that would be. The Standard Model of Cosmology is not a loose guess. It is woven from many independent threads, and they all agree. To overturn it, you would need extraordinary evidence, because you would be unravelling something that explains a great deal of what we see. Scientists are rightly cautious about claims that a deep, well-supported theory has simply broken. That caution is the key to the whole episode. In science, when a trusted theory seems to clash with a new observation, there are always two possibilities. The theory might be wrong, or the observation might be misread. History leans heavily toward the second. Again and again, a shocking result that seemed to overturn established physics turned out, on closer inspection, to rest on a hidden mistaken assumption. And in the case of the little red dots, there was one assumption sitting quietly at the base of the whole alarm. It was the assumption from the brightness problem, the idea that the dots' light was mostly starlight. Every claim that they were too massive too early depended on that single step. If the light was not mostly starlight, if much of it came from something other than stars, then the mass estimates could be wildly off, and the apparent crisis would soften. So the calm and sensible move was not to declare cosmology broken. It was to ask carefully whether the dot's light was really starlight at all. To do that, astronomers needed to stop guessing from a single colour and start reading the full spectrum of these objects, the complete spread of their light across many wavelengths. And that detailed light held more than one surprise. But before the spectra spoke, astronomers laid out the handful of stories that might explain the dots. There were broadly three. Faced with a puzzle, good scientists do not leap to one answer. They lay out the live possibilities and then test each against the evidence. For the little red dots, the field settled fairly early on three main stories. Each told a different tale about what the dots were, and each carried different consequences for our picture of the early universe. It helps to hold all three in mind because the long investigation that followed was really a slow sorting among them. The first story was the one we have already met. The little red dots are compact galaxies crowded with stars reddened by dust, and simply far more massive and mature than they should be at such an early time. Call this the starburst story, because it imagines galaxies bursting with rapid star formation. Its strength is its simplicity. Galaxies are made of stars, and a dusty, star-filled galaxy naturally looks red and bright. Its weakness is the brightness problem. Taken at face value, it demands impossible masses. The second story keeps the galaxies but changes the engine. In this version, the light is not coming mainly from ordinary stars. It is coming from a feeding black hole at the centre of each dot. When a giant black hole pulls in surrounding gas, that gas heats up and blazes with light before it falls in. A black hole shining this way is called an active galactic nucleus. Call this the black hole story. Its strength is that a single, small, intensely bright core can produce huge brightness from a tiny space, which fits the compactness perfectly. Its weakness, as we'll see, is that these dots were oddly quiet in ways that active black holes usually are not. The third story was bolder. Perhaps the little red dots were not quite like anything astronomers had named before. Perhaps they represented a new stage in the life of cosmic objects, a phase the universe passes through only at its dawn, which leaves no clear modern counterpart. Call this the new object story. Its strength is honesty. The dots really did not behave like familiar galaxies or familiar black holes. Its weakness is that something new is hard to test until you can say what specifically it is. These three stories were not entirely separate. They blurred into one another at the edges. A dot might hold both stars and a feeding black hole, with one or the other dominating its light. A new kind of object might turn out to be a feeding black hole in an unfamiliar setting. The work ahead was not to crown one story and banish the rest. It was to weigh how much each contributed, and to follow the evidence wherever it leaned. What made this sorting possible was the quality of the data. The James Webb Space Telescope does not only take pictures. With its near-infrared spectrograph, NIRSpec, and its other instruments, it can spread each dot's light into a detailed spectrum, revealing fine features that a simple image hides. Those features, the bumps and breaks and lines in the spread of light, are the fingerprints that distinguish stars from feeding black holes, dust from gas. So the investigation now had a clear shape. 3 candidate stories, a powerful instrument able to read fine detail, and a large sample of hundreds of objects to study, compare, and cross-check. The next move was to begin with the most familiar story, the starburst idea, and see how far the evidence would let it run before it strained. because the way a good theory fails is often as instructive as the way the right one finally succeeds. Let us give the first story its fair hearing. The starburst idea says that each little red dot is a small young galaxy in the middle of furious star formation wrapped in dust that reddens its light. For a while, this was a very reasonable place to start, and it is worth understanding why it fits so naturally, because a good wrong answer is built from real truths. Start with what a starburst galaxy actually is. In the present-day universe, astronomers know many galaxies that are forming stars at a frantic pace, far faster than a calm galaxy like our Milky Way. These are called starburst galaxies. They light up as countless new stars switch on at once. And crucially, vigorous star formation tends to produce a great deal of dust, because the same dense clouds that birth stars are thick with the fine grains that redden light. So a starburst galaxy is often both very bright and very red. Bright and red is exactly what the little red dots are. The early universe, too, was expected to be a busy nursery. Gas was abundant and had not yet been used up. So the idea that the first galaxies might burst with rapid star formation was not strange at all. It was almost expected. If you had asked astronomers, before the James Webb Space Telescope, what bright red compact objects in the early universe might be, many would have reasonably guessed dusty starburst galaxies. The compactness fit too, at least loosely. Early galaxies were smaller than today's grand spirals. The universe was younger and denser, and galaxies had not yet grown by merging together over billions of years. So a small, tightly packed, intensely star-forming galaxy was a believable picture. It would look compact, it would look bright, and the dust would make it look red. Some of the first careful analyses leaned this way. Researchers such as Ivo Labbé and colleagues, working with early James Webb data, modelled certain bright red sources as massive galaxies full of stars. The fits were not absurd. The light could be made to match a population of stars plus dust if you allowed the galaxy to be surprisingly massive for its age. The model worked on paper. That is what made it tempting. There was also a kind of comfort in the starburst story. It required no exotic new physics and no new class of object. It kept the little red dots inside the familiar family of galaxies. Stars make light. Dust makes red. Early galaxies are small. Done. If only the masses had been reasonable, the case might have closed there, but that if only is doing heavy lifting. The starburst story carried the brightness problem on its back the entire time. To explain the dots as starlight, you had to accept galaxies as massive as the Milky Way, or more, in place within the first few 100 million years. And not one or two of them, but a whole abundant population. The simpler the starburst story looked, the more it forced you to swallow that impossible mass. So the starburst idea was less a comfortable home than a room you could only stay in by ignoring a loud noise in the next room. It explained the colour and the brightness and the smallness, each on its own. What it could not explain, without breaking the rest of cosmology, was how so much stellar mass could exist so early. That single strain, the mass, is where the starburst story began to crack. To see exactly how it cracks, we have to look at what the numbers demand, and why packing that much star stuff into these tiny dots simply does not hold together. A theory rarely dies from a single blow. More often it strains, quietly, in several places at once, until the strain becomes too much to ignore. The starburst story strained hardest at the question of density. Not just how much mass, but how much mass crammed into how small a space. And when astronomers worked that out, the picture began to look not merely surprising, but physically uncomfortable. Recall the two clues. The little red dots are extraordinarily luminous, and they are extraordinarily compact. If all that light is starlight, then all the mass needed to produce it must sit inside that tiny point-like region. So you're not only asking for a Milky Way's worth of stars, you're asking for it to be packed into a space far smaller than the Milky Way, sometimes a region only a few hundred light-years across or less. Think about what that means for how crowded the stars would be. In the neighbourhood of our Sun, stars are spread thin, with light years of empty space between them. To fit a galaxy's worth of stars into a few hundred light years, you would need them packed thousands of times more tightly than that. The little red dots, red as pure starlight, would be among the densest collections of stars ever imagined, denser than the cores of the most crowded star clusters we know. That extreme density raises hard physical questions. Stars packed that tightly would interact strongly with one another. The whole system would be unstable in ways that are difficult to maintain. It is not obviously impossible, but it is deeply strained, and nature tends to avoid such fragile arrangements. The more carefully astronomers, including teams studying the detailed shapes of the dots, looked at the implied densities, the less comfortable the pure starlight reading became. There was a further strain in the timing, which we have met before but which bites harder here. To assemble that much stellar mass, you need many generations of stars to have formed, lived, and seeded the gas for the next generation. That is a slow process. Doing it within a few 100 million years, fast enough to be in place at cosmic dawn, pushes star formation to rates that are hard to sustain and hard to fuel. The gas supply itself becomes a problem. And then there is the matter of the dust. The starburst story leans on dust to explain the redness, but dust in turn is usually made by stars, especially by dying stars that scatter heavy elements into space. To have enough dust to redden the dots so strongly, you again need a mature history of star formation already behind you. In the very early universe, there may simply not have been enough time to build up that much dust. The redness, leaning on dust, leaned on a mature history that the early universe had not had time to provide, so the strain stacked up. Too much mass, packed too densely, built too quickly, reddened by dust that needed time the universe had not yet spent. None of these, alone, was a clean disproof. Together they made the starburst story creak loudly. It could be propped up, but only with a series of uncomfortable assumptions, each one a little harder to swallow than the last. When a story needs that much propping, scientists begin to suspect they are forcing the wrong shape into the data. The honest response was to set the assumption aside and look again at the raw evidence, the actual spread of the dot's light. And when astronomers did that, the spectra showed a striking, repeating shape that no simple galaxy of stars would naturally produce. It looked like the letter V. Now we come to one of the most beautiful clues in the whole story, and it is a shape. When astronomers spread the light of a little red dot across all its wavelengths, from the bluer end to the redder end, and plotted how bright it was at each, a distinctive form appeared again and again. The brightness was relatively flat at the bluer ultraviolet end. Then, toward the redder, infrared end, it climbed steeply upward. The dip and rise traced out a shape like the letter V, or like a check mark, with its low point in the middle. Astronomers call this overall shape of brightness across colour the spectral energy distribution, but you can simply think of it as the object's colour profile, its full fingerprint in light. And the little red dots, across the population, kept showing the same V-shaped fingerprint, flat and faint in the blue ultraviolet, then turning sharply and rising into the red. The repetition mattered. A shape this consistent, seen in object after object, is not noise. It is a defining feature of the class. The work of mapping this shape carefully was done by several teams. Researchers including David Seton and colleagues showed that this V-shaped turnover was not random. The bend, the low point where the light stops falling and starts rising, tended to occur at a very particular place in the spectrum. It happened right around a special wavelength tied to hydrogen, a feature we will meet properly soon, called the Balmer limit. The fact that the turn happened consistently at that one physically meaningful spot was a strong hint that real physics, not chance, was shaping the light. Why does a V-shape matter so much? Because different sources of light make different shapes. A simple population of young, hot stars tends to make light that is strong in the blue and ultraviolet and fades toward the red. Dust does the opposite, reddening light by suppressing the blue. a feeding black hole has its own characteristic patterns. The V-shape, with its flat blue part and its steeply rising red part, did not match any single simple source cleanly. It looked like a combination, like two different things stitched together at the bend. That hint of two parts is the key. Read the V-shape as two pieces, and a new reading opens up. The flat, faint blue part could come from one source, perhaps a modest population of stars. The steep, rising red part could come from another source entirely, something that pours out light at the redder wavelengths. The bend in the middle would then mark the handover, the place where one source gives way to the other. This is exactly the kind of clue that helps you tell the three stories apart. A pure starburst galaxy would not naturally produce this particular stitched-together shape, with its sharp turn at the hydrogen limit. Something more structured was going on. The light was carrying a message about its own origin, written in the geometry of the curve, and there was more in the spectrum than just its overall shape. Riding on top of the V were sharper features, narrow spikes and dips at specific colours, where particular elements emit or absorb light. Those features are even more diagnostic than the broad shape, because they speak directly about the gas in the object, how much of it there is, and how fast it is moving. Among those sharper features, the most telling were the lines of hydrogen, and the hydrogen lines in the little red dots were doing something dramatic. They were not narrow and crisp. They were broad, smeared out across a wide range of colours, as if something was stirring the gas to tremendous speeds. That broadening would point at first straight toward a black hole. Within the spectrum of a little red dot, certain features stand out like landmarks. The most important are the emission lines of hydrogen, the most abundant element in the universe. When hydrogen gas is energized, it glows at very specific, sharp colours. One of these, a deep red glow from hydrogen, is called hydrogen alpha. Another, a little bluer, is called hydrogen beta. These lines are among the most studied features in all of astronomy, and in the little red dots they behaved in a striking way. In a calm cloud of gas, these hydrogen lines are narrow. The gas is not moving fast, so the light comes out at a tight, well-defined colour. But in many little red dots, the hydrogen lines were not narrow. They were broad, smeared across a wide span of colour. A line that should have been a thin spike was instead a wide, rolling hill. This broadening carries information, and reading it became central to the whole puzzle. The classic explanation for a broad line is speed. If the gas producing the light is moving very fast, some of it toward you and some away, then by the same redshift and blueshift effect we met with the ambulance siren, the light gets spread across a range of colours. Gas rushing toward you shifts its light bluer. Gas rushing away shifts it redder. Mix the two, and a sharp line smears into a broad one. So a broad hydrogen line traditionally means fast-moving gas. Astronomers measure that speed from the width of the line, and in many little red dots the implied speeds were enormous, with gas apparently moving at thousands of kilometres every second. Teams led by researchers such as Jenny Green and Jorrit Matthey found broad hydrogen lines in a large fraction of these objects, often well over half of those studied closely. Such width suggested gas whipping around at a fierce pace. Now, what makes gas move that fast? In the standard reading, the answer is gravity, and a great deal of it concentrated in a small space. The most natural way to fling gas around at thousands of kilometres per second is to have it orbiting close to something extremely massive and compact. The classic such object is a black hole. Gas swirling close to a giant black hole moves at exactly these tremendous speeds, and it glows brightly as it does. This is why broad hydrogen lines have long been treated as a signature of an active galactic nucleus, a feeding black hole. When astronomers see broad lines in a normal galaxy's centre, they routinely infer a black hole stirring the gas. So when broad lines appeared in the little red dots, the natural conclusion followed at once. These dots, or many of them, seem to harbour feeding black holes at their hearts. That reading also solved the compactness beautifully. A feeding black hole produces enormous light from a tiny region, far smaller than a galaxy. So the dots could be bright and tiny at the same time, with no need for impossibly dense star fields. The black hole story suddenly looked far stronger than the starburst story. The brightness came from accretion, not starlight, and the brightness problem eased. So by this point the evidence had swung. The V-shaped fingerprint hinted at two sources of light. The broad hydrogen lines pointed to fast gas, and fast gas pointed to a black hole. The leading picture became one of small galaxies with hungry black holes at their centres. To follow that picture properly, we should pause and understand, in plain terms, what a feeding black hole actually is and why it shines. Let us slow down and build the picture of a feeding black hole carefully, because it is the engine at the centre of the leading story and it is easy to get wrong. The phrase black hole suggests something dark, something that swallows light, so it can seem strange to say a black hole could make a tiny dot one of the brightest things in the early universe. The resolution lies not in the hole itself, but in the gas around it. A black hole is a region where gravity is so strong that nothing, not even light, can escape from within a certain boundary. The black hole itself emits nothing, but black holes are rarely sitting in empty space. They are surrounded by gas, and gravity pulls that gas inward. As the gas falls, it cannot drop straight in. It swirls, forming a flattened, spinning disk around the black hole, the way water circles a drain rather than falling straight down. This swirling disk is called an accretion disk. Here is the crucial part. As the gas spirals inward, it is squeezed and sheared and heated to ferocious temperatures, often millions of degrees. Hot gas glows, and gas this hot glows fiercely, pouring out light across many wavelengths. So the region just outside the black hole becomes blindingly bright, even though the hole at the centre emits nothing. The light comes from the doomed gas in its final orbits, not from the darkness it is falling into. A black hole shining this way, fed by a bright accretion disk, is called an active galactic nucleus, often shortened to AGN. When such an engine is especially powerful, we call the object a quasar, and quasars are among the most luminous single objects in the entire universe. A quasar can outshine all the hundreds of billions of stars in its host galaxy, all from a region not much larger than our solar system. That is how a black hole can be both tiny and stupendously bright. This is exactly the combination the little red dots seem to need. A bright, compact engine, light from a region far smaller than a galaxy, and fast-moving gas swirling close to the black hole to produce those broad hydrogen lines. The active galactic nucleus idea fit the clues we had gathered with remarkable neatness. It eased the brightness problem because the light was no longer starlight and no longer demanded impossible stellar mass. It explained the compactness. It explained the broad lines. It also fit a long-standing question astronomers had been hoping the James Webb Space Telescope might help answer. Nearly every large galaxy today, including our own Milky Way, holds a giant black hole at its centre, millions or billions of times the mass of the Sun. These are called supermassive black holes. How they grew so large so early in cosmic history has been a deep puzzle. If the little red dots were small galaxies with growing black holes at their hearts, they might be showing us those supermassive black holes in the act of being born and fed. They could be a missing chapter in the story of how the giants formed. For a time then, the picture seemed to settle. The little red dots were small early galaxies, each anchored by a feeding black hole, an active galactic nucleus, glowing red and compact at cosmic dawn. It was a satisfying answer, and it connected to one of the great questions in astronomy. But satisfying answers must still pass every test. And when astronomers checked the little red dots against the other things a feeding black hole should do, they found a strange and stubborn silence. A feeding black hole is usually a noisy neighbour. It does not only glow with visible and infrared light, it announces itself in several other ways, across the spectrum, and astronomers know those announcements well from studying countless active galactic nuclei across the sky. So when the little red dots were proposed as feeding black holes, there was an obvious test. Do they make the other noises a feeding black hole should make? The answer, surprisingly, was mostly no. They were strangely quiet. The first silence was in X-rays. When gas falls into a black hole and heats to millions of degrees, the innermost hottest regions glow not only in ordinary light but in high-energy X-rays. Feeding black holes are, as a rule, strong X-ray sources. We have telescopes built to catch exactly this, most famously NASA's Chandra X-ray Observatory, which has catalogued X-ray glows from black holes across the universe. So astronomers checked. They looked for the X-ray glow that the little red dots should produce if they held ordinary feeding black holes, and for the great majority they found almost nothing. The dots were extremely weak in X-rays, far weaker than typical active galactic nuclei. The second silence was in radio waves. Many feeding black holes launch powerful jets of charged particles, and these jets blaze in radio waves that radio telescopes can detect. Again, astronomers looked, and again, for most of the little red dots, the radio glow was faint or absent. The dots were quiet in radio too. There was a third oddity, this one about change over time. Feeding black holes usually flicker. The gas falling in is turbulent, so the brightness of an active galactic nucleus tends to vary, brightening and dimming over months and years. This variability is one of the classic ways to confirm a black hole. But the little red dots, when watched, showed surprisingly little variation. They held steady, more like a calm light than a flickering fire, and the population as a whole showed little spread in their properties, as if they were all cut from a similar cloth. There was also the matter of dust again. If the dots were ordinary dust-reddened black holes, that dust should be warm, heated by the bright engine, and warm dust glows in the near and mid-infrared in a particular way. But many little red dots lack that expected glow of hot dust. The infrared light, when examined carefully by teams using the James Webb Space Telescope's mid-infrared instrument, often did not rise the way warm dust around a normal active galactic nucleus would. It behaved differently, so the black hole story, which had fit so neatly a moment ago, now faced its own loud problem made of silences. No strong X-rays, no strong radio, little flickering, no clear sign of hot dust. Each absence, on its own, might be explained away. Perhaps the X-rays were hidden behind thick gas. Perhaps the jets were weak. But the absences came together, in object after object, and together they painted a picture that did not match any ordinary feeding black hole astronomers had ever studied. This is the moment the puzzle deepened rather than resolved. The starburst story had strained on mass. Now the black hole story strained on silence. The dots looked like feeding black holes in their broad lines and brightness, yet behaved unlike any feeding black hole in their quiet. Something was different about these objects, something that let them shine like an active black hole, while staying dark in X-rays and radio. And there was one more thread to pull, perhaps the most troubling of all. Even granting a black hole its size seemed wrong. The black holes appeared far too massive for the tiny galaxies that held them. There is a quiet rule in the modern universe that astronomers have come to rely on. In galaxy after galaxy, the giant black hole at the centre and the galaxy around it seem to grow together in a steady proportion. The bigger the galaxy, the bigger its central black hole, in a fairly tight ratio. This relationship is one of the more remarkable patterns in astronomy, because it suggests that a galaxy and its black hole somehow regulate each other's growth, like two trees that always grow to matching heights. Typically, a central black hole holds something like a few thousandths of the mass of the stars in its host galaxy's central bulge. It is the small, dense heart of a much larger body. A galaxy as grand as our Milky Way holds a black hole of around 4 million times the mass of the Sun, which is large by any human measure, yet tiny compared to the hundreds of billions of stars around it. That proportion is held across a great many galaxies. It is part of what makes the universe feel orderly. The little red dots broke this rule, and broke it dramatically. When astronomers estimated the masses of the black holes inside them, from the width of those broad hydrogen lines, the black holes came out enormous, and when they estimated the masses of the surrounding stars, those came out small. The ratio was wildly off. In some dots, the black hole seemed to hold a tenth, or even close to all, of the mass of the entire stellar host, rather than a few thousandths. The black hole was not the small, dense heart of a large body. It was nearly the whole body. Astronomers called these overmassive black holes far too big for their galaxies, and they were not rare exceptions. The little red dots, as a class, seem to show some of the most extreme, overmassive black holes ever inferred. Teams studying surveys such as the James Webb Advanced Deep Extragalactic Survey, including researchers like Roberto Maiolino, found populations of these tiny, mighty black holes scattered through the early universe. This was a real problem for the simple black hole story, and it deepened the mystery in two directions at once. First, how could a black hole grow so large before its galaxy did? In the usual picture, galaxy and black hole grow together. Here the black hole seemed to have raced ahead, somehow gathering huge mass while its galaxy stayed small. That challenged the comfortable idea that they grow in lockstep. Second, the overmassive estimates fed straight back into the brightness problem, just from the other side. If you no longer needed a galaxy's worth of stars to explain the light, good. But now you needed a black hole of millions or tens of millions of solar masses, fully grown only a few 100 million years after the Big Bang. Growing a black hole that large, that fast is its own deep difficulty. You had traded one impossible-seeming mass for another. So by this stage, both leading stories were in trouble. The starburst story demanded too many stars. The black hole story demanded black holes that were too big, too early, and too quiet in X-rays and radio. Each piece of evidence seemed to rule something out without clearly ruling anything in. The little red dots were behaving like a puzzle, designed to frustrate every simple answer. And yet, buried in archival data, there was one faint signal that hinted the black hole idea was not entirely wrong. It came not from the James Webb Space Telescope at all, but from an older X-ray telescope that had been quietly watching the same patch of sky for more than a decade. Sometimes a whole debate turns on a single faint signal, noticed only because two telescopes happen to look at the same speck of sky. That is what happened with one particular little red dot, and the story of its discovery is a small lesson in how patient, layered observing can pay off years later. We have seen that the little red dots were strangely silent in X-rays. As a population, they barely glowed at the high energies that feeding black holes usually produce. That silence was one of the strongest arguments against the simple black hole story. But barely is not never. And one dot in particular broke the silence just enough to matter. The relevant patch of sky is a long, well-studied strip called the extended Graaff strip, part of a survey region astronomers have returned to again and again. NASA's Chandra X-ray Observatory, which launched back in 1999, had been observing that strip for years, building up a deep map of its X-ray sources. Among the millions of X-ray points Chandra has catalogued across the sky, one in that strip carried a label as plain as a license plate, a catalogue name marking its position in the survey. For more than 10 years, that X-ray source sat quietly in Chandra's archive, just one faint glow among many. No one knew it was special. Then the James Webb Space Telescope observed the same field, found the little red dots, and astronomers began matching positions. And there it was. One of the little red dots sat at exactly the same spot on the sky as that old, faint Chandra X-ray source. The two were the same object, seen by two very different telescopes years apart. The Princeton University astronomer Andy Goulding, describing the find, captured the feeling of it well. The X-ray dot had been resting in the Chandra survey data for over a decade, but no one had any idea how remarkable it was until the James Webb Space Telescope came along to observe the field. The new infrared eyes gave meaning to an old, overlooked signal. Why did this single match matter so much? Because the energy of that X-ray glow was the kind produced by a feeding black hole, similar in character to the X-rays from quasars, those most luminous of active galactic nuclei. Here then, was direct evidence that at least this little red dot truly did host a growing supermassive black hole. The broad hydrogen lines had hinted at a black hole. This X-ray whisper confirmed one, in at least this case, with an entirely independent kind of measurement. That single detection did important work. It told astronomers that the black hole idea was not simply wrong. These objects really could harbour feeding black holes. The near-total X-ray silence of the population was therefore not proof that there were no black holes. It was more likely a clue that the black holes were somehow hidden, their X-rays smothered before they could escape. And that idea of a black hole somehow buried, its usual signals muffled, would turn out to be close to the heart of the answer. To muffle X-rays and radio, to steady the flicker, to redden the light, you would need to wrap the black hole in something thick, something dense, something that could reprocess the fierce light of the engine into the soft red glow seen in the dots. The clue, in other words, was pointing toward gas, a great deal of gas packed densely around the black hole. To follow it, we must look again at that V-shaped fingerprint, and at one sharp feature within it that everyone had first read as a sign of old stars. Within the V-shaped fingerprint of the little red dot sits one particular feature that became the hinge of the entire mystery. It is a sharp step in the light, a place where the brightness suddenly changes as you move across the spectrum. Astronomers call it the Balmer break, and to understand the whole answer, you need to understand this one step, because everyone read it one way at first, and that reading turned out to be the wrong door. Begin with hydrogen, the simplest and most common atom in the universe. A hydrogen atom is a single proton with a single electron, and that electron can sit at different energy levels, like rungs on a ladder. When the electron jumps between rungs, it absorbs or emits light at very specific colours. A whole family of these jumps, those involving the second rung, produces features in the visible part of the spectrum, and that family is named after the physicist who first described it, Johann Balmer. The Balmer break is a sudden drop in light at a particular wavelength tied to that second rung. Below a certain colour, hydrogen gas can absorb light very efficiently, soaking up the bluer photons. Above that colour it cannot. So as you scan across the spectrum, you can hit a sharp edge, a step where the light drops off, because beyond that point the hydrogen has been busily absorbing. That step is the Balmer break, and its presence and sharpness say something about the gas and the light source behind it. For decades, the Balmer break has carried a fairly standard meaning. A strong Balmer break is classically the mark of a population of older, cooler stars. In an aging galaxy, where the hottest, bluest stars have already burned out, and only the longer-lived, cooler stars remain, the combined starlight shows a pronounced Balmer break. So when astronomers see a strong break, the trained instinct is to say, there sits a settled population of older stars. This is exactly what the little red dots seem to show. Many of them displayed clear, sometimes very strong Balmer breaks. Teams measuring these objects, including the work mapping that V-shaped turnover, found that the bend in the V tended to fall right at the Balmer break. The natural reading followed at once. The dots must contain a substantial population of older stars, which meant they must be fairly mature galaxies, which dragged the whole problem straight back toward the impossible mass version of the starburst story. So the Balmer break became a kind of trap. Read it the classical way, as the signature of old stars, and you were forced back into demanding a large, mature stellar population formed impossibly early. The very feature that should have clarified things instead seemed to reinforce the worst version of the puzzle. The dots looked, by this measure, like old, massive galaxies at a time when no old, massive galaxies should exist. But there was a quiet assumption hiding inside that classical reading, the same kind of hidden assumption we met when worrying that cosmology had broken. The assumption was that a Balmer break can only be made by stars. That assumption felt safe because, in the nearby universe, it usually is. Old stars are the familiar cause, so a break means old stars. Case closed. The trouble is that the little red dots are not the nearby universe. They are extreme objects at cosmic dawn, packed with dense gas in unfamiliar conditions, and it turned out that there is another way to make a Balmer break, one that has nothing to do with old stars at all. That alternative would crack the trap wide open. The breakthrough in reading the Balmer break came not from finding new data, but from asking a sharper question of the old data. The question was simple: is there any way, other than a population of old stars, to produce a strong Balmer break? And the answer, worked out carefully by theorists, was yes. Dense gas can do it too. That single realization reopened the entire case. The key insight came from researchers studying how light behaves when it passes through extremely dense hydrogen gas. Among them were Kohei Inayoshi and Roberto Maiolino, who showed that if you surround a bright source with a thick enough shroud of hydrogen, the gas itself can carve a Balmer break into the light, with no old stars required at all. The break in this picture is not a fingerprint of age, it is a fingerprint of density. To see how, recall what the Balmer break is. It is absorption by hydrogen atoms whose electrons sit on that second rung of the energy ladder. In an ordinary thin gas, very few hydrogen atoms have an electron parked on the second rung at any moment, so the effect is weak. But if the gas is extraordinarily dense and bathed in intense radiation from a bright central engine, a much larger fraction of the hydrogen atoms can be kept in that second rung state. With so many atoms ready to absorb, the gas carves a strong Balmer break into the light passing through it. This is a genuinely different reading of the same feature. In a normal aging galaxy, a strong break means many old stars. But around a brilliant black hole wrapped in a dense hydrogen shroud, a strong break means a great column of energized gas. Same step in the spectrum, completely different cause. One points to a slow, mature population of stars, the other points to a young, fierce engine buried in thick gas. And notice how beautifully this alternative reading fits the silences we found earlier. A black hole wrapped in a dense shroud of gas would have its X-rays absorbed before they could escape, explaining the X-ray silence. Its flickering would be smoothed out by the surrounding cocoon, explaining the steadiness. The thick gas would reprocess the fierce engine light, reddening it, explaining the colour without needing dust. The very same dense gas that makes the Balmer break would muffle all the signals that had seemed so puzzling. The same dense gas could also explain another odd feature astronomers had noticed. In some little red dots, the hydrogen lines showed not only emission but absorption, as if light were passing through a thick layer of hydrogen on its way out. That is exactly what a dense gas shroud would do. Light from the central engine would shine outward and be partly absorbed by the surrounding hydrogen, leaving absorption marks. Researchers studying objects with these features, like Vasily Kokorev and others, found this pattern again and again. So the reinterpretation did not just rescue the black hole idea. It unified the evidence. The broad lines, the Balmer break, the X-ray silence, the radio quiet, the steadiness, the missing hot dust, the absorption features. All of them could flow from a single picture. A black hole, feeding, wrapped in an extraordinarily dense cocoon of gas. This picture needed a name, something that captured how strange it was, this marriage of a black hole and a thick glowing shell. The name that emerged was vivid and a little startling. Astronomers began to call these objects black hole stars, and that name points to the heart of the answer. The phrase black hole star sounds like a contradiction. A black hole is the darkest thing in the universe. A star is a glowing ball of gas. Putting the two words together seems almost playful, but the name captures something real and precise about what the little red dots appear to be, and once you see the picture, the strange name makes perfect sense. Here is the picture. At the centre sits a black hole, feeding on gas, an active engine pouring out fierce light from a tiny region. But unlike an ordinary feeding black hole sitting in relatively open space, this one is buried. It is wrapped in an enormous dense cocoon of gas, a thick shroud of hydrogen so opaque that the light from the engine cannot simply shine straight out. Instead, the light pushes its way through the cocoon, heating it scattering within it and emerging from the outer surface transformed. Now think about what that outer surface looks like from far away. You do not see the black hole, you do not see the bright engine directly, you see the glowing outer skin of the cocoon, a vast shell of hot gas radiating light. And a glowing shell of hot gas radiating from its surface is, in its outward behaviour, very much like the surface of a star. A star, after all, is a ball of gas glowing from its surface. So an object that is a black hole hidden inside a glowing gas envelope mimics, from the outside, the appearance of an enormous star, hence the name black hole star. The scale of these objects in this picture is remarkable. The cocoon of gas can stretch across something like 10 million kilometres, and the whole structure glows with the reprocessed power of the feeding black hole within. It is as if nature took the engine of a quasar and wrapped it in the body of a giant star, producing something that belongs fully to neither category and sits strangely between them. This model does a great deal of work. It explains the red colour, because light forced through a thick gas cocoon emerges reddened and softened. It explains the compactness, because the whole thing is small, a point of light rather than a sprawling galaxy. It explains the X-ray and radio silence, because the cocoon absorbs and smothers those signals. It explains the steadiness, because the thick shroud smooths out the engine's flicker. And it explains the Balmer break and the absorption features, because they arise naturally in dense hydrogen gas. Several teams converged on versions of this idea, working from different angles. Theorists showed that a black hole inside a thick gas envelope would settle into a structure with a glowing photosphere, an outer radiating surface much like a star's. Observers found objects whose spectra matched this picture in striking detail. The black hole star model began to look less like a wild guess, and more like the shape the evidence had been pointing toward all along. But a good model has to do more than explain features in words. It has to make sharp, testable predictions about the actual numbers in the light, and survive when those numbers are measured precisely. The black hole star idea made exactly such a prediction, and it was a surprising one. It said that the broad hydrogen lines, the ones that had been read as fast-moving gas around a giant black hole, might not be telling us about speed at all. To see why, we have to look closely at what happens to light when it bounces, again and again, off the free electrons in a dense, ionized cocoon. Here is the subtle idea that turned the whole picture, and it rewards a slow, careful walk. We have been assuming all along that the broad hydrogen lines in the little red dots meant fast-moving gas, and that fast-moving gas meant a very massive black hole. But the black hole star model offered a different reason a line might be broad, one that has nothing to do with how fast the gas is moving. It is about how much the light bounces on its way out. To understand it, picture the dense cocoon of gas around the black hole. This gas is ionized, which means it has been energized so strongly that the electrons have been stripped away from their hydrogen atoms and are floating free. The cocoon is therefore full of free electrons packed densely, and free electrons are very good at one particular thing: they scatter light. A photon of light travelling through such a cloud does not fly straight out. It strikes an electron, bounces off in a new direction, strikes another, bounces again, and zigzags its way slowly toward the surface, ricocheting countless times before it escapes. Now, here is the key. Each time a photon bounces off a moving electron, its colour shifts very slightly, by that same stretching and squashing effect we met with the ambulance siren. The electrons are jittering about with the heat of the gas, so each bounce nudges the photon's colour a tiny bit one way or the other. A single bounce barely matters. But in a dense enough cocoon, a photon may bounce thousands of times before it escapes, and all those tiny random colour nudges add up. A photon that started at one sharp colour comes out smeared across a range of colours. This means a spectral line can be made broad without any fast bulk motion of gas at all. The line is broadened by the bouncing, by electron scattering, not by orbital speed. The underlying gas could be moving relatively slowly, but the relentless ricocheting of light through the dense cocoon smears the sharp line into a broad one. The breadth is a record of how many times the light bounced, not how fast the gas was orbiting. This is the crucial insight, worked out carefully by researchers including Vadim Rusakov and Darach Watson of the Cosmic Dawn Center in Copenhagen, along with their colleagues, and supported by other teams reaching similar conclusions. They examined the highest quality spectra of little red dots and found that the broad lines had a particular shape, a sharp, narrow core with smeared out wings, which is exactly the fingerprint of electron scattering rather than bulk motion. The shape of the broadening itself revealed its true cause, and there was more in the detail. The data required the cocoon to be extraordinarily dense in electrons and extraordinarily compact, with the light coming from a region only light days across. That is tiny, far smaller than a galaxy, smaller even than the distance from our Sun to its nearest neighbour star. Such enormous density and luminosity packed into so small a space could only be powered, the researchers argued, by gas accreting onto a black hole. The black hole was confirmed, but its broad lines were lying about its mass, because if the broad lines come mostly from bouncing light, not fast orbiting gas, then the old way of weighing the black hole, using the line width as a measure of orbital speed, would give the wrong answer. It would mistake the bouncing for speed, and speed for gravity, and gravity for mass. The black holes would look far more massive than they truly are, and when astronomers corrected for the bouncing, the masses fell dramatically. We have arrived at the centre of the answer, the quiet turn that resolves so much of the mystery. It is this. The little red dots do hold feeding black holes, but those black holes are far smaller than astronomers first believed, perhaps around 100 times smaller. The fearsome, overmassive black holes that seem to break the rules were, in large part, an illusion created by bouncing light. Recall how the black hole masses had been estimated. You measure the width of the broad hydrogen line. You assume that width comes from gas orbiting at high speed. You use that speed, with the laws of gravity, to work out how much mass must be at the centre to fling the gas around so fast. Wide line, fast gas, big mass. That was the chain. And it gave black holes of hundreds of millions, even billions, of solar masses, terrifyingly large for the early universe. But we've just seen the flaw. The line width does not come mainly from fast orbiting gas. It comes mainly from light bouncing off free electrons in a dense cocoon. So the first link in the chain was wrong. The gas was not orbiting nearly as fast as the line width implied. When the researchers, led by Vadim Rusakov and Darach Watson and their colleagues, accounted for the electron scattering and measured the true narrow core of each line, they found the real orbital speeds were far lower, and lower speeds mean a far smaller central mass. How much smaller? Their work, published in the journal Nature, found that correcting for the bouncing reduced the implied black hole masses by roughly a factor of 100. Instead of black holes of hundreds of millions or billions of solar masses, the little red dots appear to hold black holes in the range of about 100,000 to 10 million times the mass of the Sun. As Darach Watson described it, these are young black holes, far less massive than people had believed, enshrouded in a cocoon of gas that they are consuming in order to grow. A factor of 100 is the difference between a crisis and a non-crisis. A black hole of 10 million solar masses a few 100 million years after the Big Bang is not impossible. It fits reasonably well within our understanding of how black holes grow. It is large but not absurd. The truly impossible objects, the billion solar mass giants that should not exist so early, were never really there. They were an artifact of misreading bouncing light as speed. This is why the answer is so satisfying and so calm. It does not require throwing out cosmology. It does not require exotic new physics or a broken universe. It requires noticing one subtle effect, electron scattering in a dense cocoon, and correcting for it. Once you do, the monstrous masses shrink to reasonable ones, and the alarm fades. As Watson put it, We no longer need to invoke completely new types of events to explain these objects. They are strange, but they are not lawless. It is worth dwelling on how human this story is. For a few years, the little red dots seemed to threaten our deepest theory of the cosmos, and the resolution came not from a grand revolution, but from careful attention to the shape of a spectral line and the humble physics of light bouncing off electrons. The universe had not broken its rules. We had simply misread one of its messages. So the black holes are real, but modest. The cocoon is real and dense. And the cocoon, it turns out, is also the source of the very thing that named these objects in the first place, their red colour. We named these objects for their colour before we understood it. Little red dots. The red was the first thing anyone noticed, and for a long time it was explained, hesitantly, by dust. But the black hole star picture offers a cleaner reason for the redness, one that flows directly from the cocoon itself. The dots are red because of how light escapes a thick shroud of gas, and understanding this closes a loop that has been open since the first chapter. Start at the centre. The feeding black hole pours out fierce, energetic light, much of it at the bluer, higher energy end of the spectrum, the kind of light a hot accreting engine naturally produces. If that light could escape directly, the object would not look red at all. It would look blue and brilliant like a naked quasar. But it cannot escape directly. It is trapped inside the dense cocoon of gas, and to reach us, it must work its way out through that thick shroud. As the fierce engine light pushes into the cocoon, it heats the gas and is absorbed and re-emitted again and again. The gas takes in the high-energy light and radiates it back out at lower energies, at longer, redder wavelengths. This is a general habit of nature. Energy passed through a thick absorbing medium tends to come out softer and redder than it went in. By the time the light finally emerges from the outer surface of the cocoon, much of its original blue fierceness has been reprocessed into a warmer, redder glow. As Dari Watson described the process, the black hole consumes the surrounding gas and generates enormous heat, and that heat shines through the cocoon. It is precisely this radiation, working its way through the shroud, that gives the little red dots their distinctive red colour. The redness is not dust in the foreground. It is the signature of light escaping from inside a dense, hot envelope. The colour is the cocoon itself glowing. This also explains why the redness is so consistent across the population. If the red came from dust, you would expect a great deal of variation, since different galaxies hold different amounts of dust in different arrangements. But if the red comes from the basic physics of light escaping a dense gas cocoon, then every black hole star would redden its light in much the same way, for the same reason. The uniform redness, which had been a puzzle, becomes a natural consequence of a shared structure. And recall the V-shaped fingerprint from earlier, with its flat blue part and its steeply rising red part. The black hole star picture reads that shape cleanly. The steep red rise is the reprocessed glow of the cocoon, the heat shining through the shroud. The flat blue part may be a smaller contribution, perhaps a modest amount of starlight from the surrounding galaxy, or light leaking through. The bend in the middle, at the Balmer break, marks where the dense hydrogen gas carves its step into the spectrum. Every part of the fingerprint now has a cause, so the name we chose at the very beginning, little red dots, turns out to point straight at the physics. They are little because the black hole and its cocoon are compact. They are red because the light is reprocessed and softened by the gas it escapes through. And they are dots because all of it is packed into a tiny point of light. The plain name, chosen before anyone understood, described the deepest truth of the objects. With the general picture in place, it helps to meet a few of these objects up close, the specific dots whose detailed spectra clinched the case. The first is an object with a Balmer break so sharp that astronomers gave it a fittingly dramatic name. It is one thing to build a model in general terms. It is another to test it against a single, well-studied object, and watch it either hold or fall apart in the details. One of the most important test cases for the black hole star idea is a little red dot with a Balmer break so steep and so clean that astronomers nicknamed it the Cliff. The name fits. Its spectrum shows a drop so sharp it looks like the edge of a cliff face. The Cliff was found through one of the surveys dedicated to studying these red objects, a program called the Red Unknowns, Bright Infrared Extragalactic Survey, known by the short name RUBIES. This survey, led by Anna de Graaff and Gabriel Brammer, deliberately set out to observe a few hundred very red sources with a spectrograph aboard the James Webb Space Telescope, gathering high-quality spectra precisely so that objects like the Cliff could be studied in fine detail. RUBIES became one of the richest hunting grounds for understanding the little red dots. What makes the Cliff so valuable is the strength of its Balmer break. In most objects, the break is present but moderate. In the Cliff, it is extreme, one of the most pronounced ever seen. And as we have learned, a Balmer break that strong is very hard to make with old stars alone. You would need an implausible population. But it is exactly what you would expect from an enormous column of dense hydrogen gas, energized and stratified around a central engine in the black hole star picture. When astronomers examined the Cliff closely, they found that the simplest, most natural explanation for its combination of features, the towering Balmer break, the emission lines, and the absorption signatures of hydrogen, was not a galaxy of old stars, but a black hole wrapped in dense gas. The Cliff was, in other words, a clean example of a black hole star, an object whose spectrum almost demanded the new model and resisted the old ones. The absorption features mattered especially. In the Cliff, and in objects like it, astronomers saw signs that light was passing outward through a thick layer of hydrogen, leaving the marks of that hydrogen pressed into the spectrum. That is precisely the fingerprint of a dense shroud surrounding a central light source. The light shines out from the engine, crosses the dense gas, and arrives at our telescopes carrying the imprint of everything it passed through. The Cliff wore that imprint plainly. The Cliff also helped tie the broader population together. Astronomers noted that objects with very strong Balmer breaks, like the Cliff, also tended to show the other signatures the model predicted, linking break strength, hydrogen absorption, and the electron scattering shape of the broad lines into a single consistent family. These were not unrelated quirks. They were different faces of the same underlying structure, a black hole in a dense ionized cocoon, seen from slightly different angles or at slightly different stages, so the Cliff served as a kind of cornerstone. It was extreme enough to rule out the easy answers and clean enough to point clearly at the black hole star model. A single well-chosen object, studied deeply, did what 1,000 blurry images could not. It let astronomers see the machinery up close. But even the Cliff had its limits. Its spectrum, though sharp, did not show every predicted feature at once. To find an object that displayed nearly the whole set of fingerprints together, in one place, astronomers needed a stroke of luck, and they got it, in the form of a distant dot whose light was magnified by the gravity of an entire foreground cluster of galaxies. To truly nail down what a little red dot is, astronomers needed an object bright enough and clear enough to show many predicted features at once, all in a single deep spectrum. The trouble is that these dots are faint and far, but the universe on occasion lends a hand through a trick of gravity that turns distant galaxies into natural magnifying lenses. One such lens delivered the clearest view of a black hole star yet obtained. The trick is called gravitational lensing. According to Albert Einstein's theory of gravity, mass bends the path of light. A massive cluster of galaxies sitting between us and a more distant object acts like a giant, if imperfect, lens. Light from the background object is bent and focused as it passes the cluster, arriving at our telescopes brighter and more magnified than it otherwise would. When a little red dot happens to sit behind such a cluster, its faint light is amplified, and we can study it in far greater detail than usual. This is what happened with a particular lensed little red dot, whose light was magnified enough that the James Webb Space Telescope could record an exceptionally deep spectrum of it. The result was the richest spectrum of such an object yet taken, showing more than 40 distinct spectral lines and features. most precious of all, those features pointed again and again in the same direction toward the black hole star model. As one of the researchers involved, Vasily Kokorev, noted, none of the previous little red dots had shown all of the pieces of evidence gathered in the same place at once. What did that deep spectrum reveal? It showed emission from elements arranged in a way that did not fit a simple rotating cloud of gas, but did fit the scattering of light by free electrons in a dense cocoon, exactly the bouncing light effect at the heart of the answer. It showed signs of fluorescence, where gas glows after being lit by radiation, and absorption by helium, both pointing to a dense, energized shroud. Feature after feature lined up with the picture of a black hole buried in thick gas. Interestingly, this lens dot showed a somewhat weaker Balmer break than the most extreme examples like the cliff. At first, that might seem to complicate things, but the researchers offered a natural reason. This particular object appeared to sit within a larger host galaxy than usual, and the extra starlight from that galaxy partly filled in the break, softening it. Rather than breaking the model, this detail extended it, showing how the same kind of object could look slightly different depending on its surroundings. The overall lesson was one of convergence. Here was an object where, thanks to the lucky magnification of gravitational lensing, astronomers could see nearly the whole predicted set of features together, and they fit. As Kokorev put it, everything fit, nothing was broken, and that, he suggested, makes the puzzle of our universe even better rather than worse. The clearest view yet was also the most reassuring. This object, and others like it, moved the black hole star idea from a promising model to a well-supported explanation. The little red dots are feeding black holes, modest in mass, wrapped in dense, glowing cocoons of gas. The deep lensed spectrum was as close to seeing that structure directly as the current evidence allows, and yet to understand these objects fully, it helps to look at an extreme case from the opposite direction, a little red dot that seems to be almost all black hole and cocoon, with hardly any surrounding galaxy of stars at all. Astronomers gave it a memorable description. They called it a naked black hole. Most galaxies present their central black hole the way a ring presents its jewel, surrounded by a broad band of stars, the black hole a small bright point set within a much larger stellar body. But among the little red dots, astronomers found an object that breaks this pattern in the most striking way. It appears to be almost all black hole and cocoon, with very little surrounding galaxy of stars at all. They described it as a naked black hole, and it sharpens our understanding by showing the engine with almost nothing else around it. The object sits behind a massive cluster of galaxies called Abell 2744, which, like the lens dot we just met, helps magnify the faint light behind it. The little red dot itself, at a redshift placing it only about 700 million years after the Big Bang, carries a catalogue name marking it as a quasar-like source in that field. What made it remarkable was not its brightness, but its surroundings, or rather, the near absence of them. When astronomers studied this object, they found the strong signatures of a feeding black hole, the broad lines, the compact bright engine, but almost no sign of a surrounding population of stars. In most galaxies, the central black hole is dwarfed by the mass of stars around it. Here, the stars were so faint, so scarce, that the black hole seemed to dominate almost everything. It was as if the jewel had arrived without its ring, the engine without its galaxy. This is why the description naked fits so well. The black hole and its cocoon were laid bare, with little stellar clothing around them. And that bareness is scientifically precious, because it lets astronomers study the engine and its cocoon with the least possible confusion from starlight. When you want to understand a machine, it helps to find one with the casing removed. A naked black hole also speaks directly to one of the deepest questions raised by the little red dots, the question of which came first, the black hole or the galaxy. In the present-day universe, black holes and galaxies grow together in that steady proportion we met earlier. But an object that is almost all black hole, with barely any galaxy yet around it, suggests that, at least sometimes, the black hole can come first. The black hole may have started growing early and fast, gathering mass before its galaxy had time to assemble around it. That ordering black hole first, galaxy later, would help explain the overmassive appearance of the dots, even after the mass corrections. If a black hole gets a head start, growing while its galaxy is still small, then for a while the black hole will look too big for its host, simply because the host has not caught up yet. The naked black hole is a snapshot of that early head start, caught in the act. So this single extreme object, almost all engine and cocoon, does double duty. It strips away the starlight and lets astronomers study the black hole star in its purest form, and it hints at an answer to the chicken and egg question of black holes and galaxies, suggesting that in these early objects the black hole led the way. With these specific objects studied, the cliff, the lens dot, the naked black hole, the general picture stands on firm ground. And with that picture in hand, we can finally return to the fear that started so much of this. The worry that the little red dots had broken our understanding of the cosmos and lay it gently to rest. We can now return, with a calmer mind, to the fear that haunted the early years of this story. The little red dots, it was said, might break cosmology. They seem too massive, too bright, too early, threatening the careful, well-tested model of how the universe grows. With the black hole star picture in hand, we can see clearly why that fear, though reasonable at the time, has largely dissolved. The fear rested on two pillars, and both have crumbled gently. The first pillar was the assumption that the dot's light was mostly starlight, which forced impossible stellar masses. But we now understand that much of the light comes from a feeding black hole and its glowing cocoon, not from a vast population of stars, so the demand for impossible stellar masses simply goes away. You do not need a Milky Way's worth of ancient stars formed in a few 100 million years. You need a modest black hole in a bright shroud of gas. The second pillar was the apparent existence of monstrous, overmassive black holes, billions of times the mass of the Sun, fully grown impossibly early. But we have seen that those masses were largely an illusion, created by reading bouncing light as fast motion, correct for the electrons scattering in the cocoon, and the black holes shrink by about 100-fold, into a range of perhaps 100,000 to 10 million solar masses. Black holes of that size, at that early time, fit reasonably within our understanding of how black holes grow from their seeds. No rule is broken. So both pillars of the crisis were built on hidden assumptions about how to read the light. Once the light was read correctly, accounting for the dense cocoon and its scattering, the crisis evaporated. As the researchers behind the key measurements emphasized, the universe had not broken its own rules. We had simply misunderstood one of its more subtle messages. The standard model of cosmology, woven from many independent threads, stands intact. This is worth dwelling on, because it is a quiet triumph of careful science over alarm. When the dots first appeared, the dramatic headline was that they might overturn cosmology. The less dramatic and ultimately correct response was to suspect a misread measurement and to look harder. History, again and again, rewards that patience. Extraordinary claims of broken physics usually resolve into ordinary physics, seen more clearly. The little red dots followed that path exactly. There is even a sense in which the dots, far from breaking cosmology, have enriched it. They have revealed a whole population of early feeding black holes that we did not know existed, caught in an unusual and short-lived phase, wrapped in dense gas. They have shown us black holes growing at cosmic dawn, possibly before their galaxies, offering a new window onto one of the great mysteries, the origin of the supermassive black holes that anchor galaxies today. The dots did not weaken our picture of the universe. They added a striking new chapter to it, so the alarm can be set down. The little red dots are not a sign that our understanding has collapsed. They are a sign that our newest telescope can see things our theories had not yet imagined in detail, and that, with care, those things can be understood within the framework we already trust. The universe remains lawful. It is simply richer and stranger than we had seen, but understanding what the dots are raises a deeper question we have so far set aside. If these are young black holes of 100,000 to 10 million solar masses growing at cosmic dawn, then where did they come from? How does a black hole get that big, that early, in the first place? That question reaches back to the very first generation of objects in the cosmos. Every black hole begins as a seed, a smaller mass that then grows by feeding. So if the little red dots are young black holes of 100,000 to 10 million solar masses, present only a few 100 million years after the Big Bang, we must ask where their seeds came from and how those seeds grew so quickly. This is one of the deepest open questions in astronomy, and the little red dots have given it fresh urgency. There are broadly two ideas about how the first black hole seeds formed, and astronomers often call them light seeds and heavy seeds. The difference is just how massive the seed was to begin with, and each path has its strengths and its difficulties. The light seed idea starts small. The very first stars in the universe, formed from pure hydrogen and helium with no heavier elements, are thought to have been enormous, far larger than most stars today. When such a giant early star died, it could collapse into a black hole of perhaps a few 100 times the mass of the Sun. That is a light seed. The trouble is that growing from a few 100 solar masses up to millions in only a few 100 million years is a tight race. The black hole must feed almost continuously at the maximum sustainable rate the whole time with little room to spare. The heavy seed idea starts big and skips the star entirely. In certain special conditions in the early universe, a vast cloud of gas might collapse directly into a black hole without first forming a star at all. This is sometimes called direct collapse, and it could produce a seed of tens of thousands, or even 100,000, solar masses right at the start. A heavy seed has a much easier time growing to the observed sizes because it begins most of the way there. The difficulty is that the special conditions for direct collapse are demanding, and may have been rare. The little red dots speak to this debate in an interesting way. Because the black hole star picture lowered their masses by about 100-fold, the dots no longer demand the most extreme, fastest possible growth. A black hole of a few million solar masses at cosmic dawn is far easier to explain than a billion solar mass giant. Either a light seed feeding steadily, or a more modest heavy seed, could plausibly reach these sizes in the time available. The mass correction did not just calm the cosmology fear, it also relaxed the demands on how black holes are born. The naked black hole we met earlier adds another clue. If black holes can grow early, even before their galaxies assemble around them, that points towards seeds that form readily and feed efficiently in the dense gas of the early universe. The dense cocoons themselves may be part of the answer. A black hole swaddled in thick gas has an abundant food supply right at hand, and can grow steadily by consuming the very cocoon that surrounds it, as Derek Watson described, eating it from the inside. So the little red dots may be more than a solved puzzle. They may be a tool for studying the birth of supermassive black holes, a population caught in the act of early rapid growth, their seeds still close behind them. The question of light seeds versus heavy seeds is not yet settled, and the dots will likely help decide it. Before we follow the dots forward to their fate, there is one more twist worth telling, an honest and slightly humbling one. Part of the original alarm came not from the dots themselves, but from the telescope that found them, which turned out to be even better than its makers expected. Here is a detail that rarely makes it into the popular telling of the little red dots, and it is worth including, because it is honest and a little humbling. Part of the original alarm, the sense that the dots were too bright, came not entirely from the dots themselves, but from the telescope that found them. The James Webb Space Telescope turned out to be better than its own designers expected, and that excellence, oddly, contributed to the early confusion. When astronomers measure how bright an object is, they rely on knowing exactly how their telescope performs. They need to know how much of the incoming light the instrument actually captures and focuses. If the telescope performs exactly as designed, the brightness measurements are straightforward. But if the telescope quietly performs better than designed, capturing and focusing more light than expected, then early measurements can overstate how bright the objects truly are until the telescope's real performance is fully understood. That is part of what happened. The James Webb Space Telescope's optics turned out to be sharper and more efficient than their already demanding specifications required. The mirror, the alignment of its 18 golden segments, the whole optical system simply overperformed. So in the earliest analyses, some of the apparent extra brightness of the little red dots was not intrinsic to the dots at all. It was the telescope being better than assumed, gathering more light than the early calculations expected. As the real performance was pinned down, a portion of the puzzling excess brightness quietly resolved into a calibration detail. This did not explain the dots away. They are still genuinely remarkable objects. But it shaved off a piece of the original alarm, reminding everyone that part of too bright too early was really, we have not yet perfectly understood our new instrument. It is a small lesson in humility. When a brand new telescope shows you something shocking, some of the shock may be the telescope, not the universe. There is a second related subtlety that often goes unmentioned, and it concerns the faint glow of our own solar system. Even far out at the second Lagrange point, a telescope looking at the deep sky must peer through a thin haze of dust scattered throughout our solar system. Sunlight scattering off that dust produces a soft background glow called zodiacal light. This faint foreground sets a kind of floor on how cleanly faint objects can be measured, and it cannot easily be removed. It is a reminder that even our finest deep images are taken from inside a dusty solar system looking out. Neither of these details overturns the story of the little red dots. The dots are real, the black holes are real, and the cocoons are real. But these subtleties matter, because they show how science actually works. A surprising result arrives. People sound the alarm, and then, piece by piece, the surprise is taken apart, with some of it turning out to be the objects themselves, some of it the instrument, and some of it the dusty window we observe through. The truth emerges from sorting these apart with patience. With those honest caveats noted, we can ask a question that brings the story closer to home. If the little red dots were real objects at cosmic dawn, are there any like them nearby in the present-day universe where we might study them in far greater detail? The search for local lookalikes has begun, and it has already turned up something. One of the strangest facts about the little red dots is that they seem to belong only to the distant past. They flourished at cosmic dawn and then largely vanished, with no clear examples nearby. That absence was part of their mystery, but it also offered a tantalizing possibility. If even a few lookalikes could be found closer to home, in the nearby universe, astronomers could study them in far greater detail than the faint far ones allow, and test the black hole star picture directly. The hunt for such local analogues has begun, and it has already turned up promising candidates. Researchers, including work led by Xiaojing Lin and colleagues, have reported finding objects in the more nearby universe that share key signatures with the distant little red dots, in particular the marks of cool, dense gas envelopes surrounding a central source. These local lookalikes appear to carry the same kind of dense gas cocoon that the black hole star model predicts, but close enough to examine more closely. Why does proximity help so much? Because nearby objects are brighter and easier to resolve. With a distant little red dot, even the mighty James Webb Space Telescope sees only a faint point and must work hard to extract a spectrum. A nearby analogue can be studied with many telescopes across many wavelengths in fine detail. If you want to understand a rare bird, it helps enormously to find one in your own garden, rather than only glimpsing it through a telescope on a far mountain. The existence of local lookalikes also softens one of the odder features of the story, the apparent total disappearance of the dots after the early universe. Perhaps they did not vanish entirely. Perhaps a small number of similar objects or related phases persist at low levels even now, rare leftovers of a process that was once common. Finding them nearby suggests the black hole star phenomenon is not strictly locked to cosmic dawn, even if it was overwhelmingly more common then. There is a deeper reason these local analogues matter, tied to how science builds confidence. Earlier we noted the danger of judging far-off objects only by what we can see nearby, of assuming the hidden part of the iceberg matches the visible tip. Local lookalikes let astronomers turn that around. They can study a nearby example in full, learn how its dense gas cocoon behaves, and then carry that detailed understanding back out to the distant dots. The near and the far inform each other. It is worth being honest that this work is young and ongoing. Confirming that a nearby object is truly the same kind of thing as a distant little red dot is delicate, and astronomers are still checking and debating. But the early findings are encouraging. They suggest that the black hole star, far from being a peculiarity of one strange era, is a real physical configuration that nature can assemble and that we may be able to study up close. So the little red dots are slowly losing their isolation in time. Once they seemed to belong solely to the distant dawn, glimpsed only as faint old light. Now there are hints of their relatives closer to home, where the dense gas cocoon and the buried black hole might be examined in detail. Which leaves one large question still open about the distant dots themselves. If they flourished at cosmic dawn and then faded, where exactly did they go? What becomes of a black hole star when its brief, bright phase ends? We have followed the little red dots from their first surprising appearance to an understanding of what they are. But a puzzle still lingers from early in the story. The dots flourished at cosmic dawn, peaked around 900 million years after the Big Bang, and then, by roughly 1.5 billion years, largely disappeared. They are creatures of the early universe with no obvious counterpart in the grown-up cosmos. So where did they go? The most natural answer is that they did not vanish so much as change. A black hole star is, by this picture, a brief phase, not a permanent state. It is what you see when a young black hole is buried in an unusually dense cocoon of gas, feeding rapidly. But such a phase cannot last forever. The black hole consumes its surroundings. The dense gas is used up or blown away, or settles into a more ordinary structure. And when the cocoon thins, the object stops looking like a little red dot. It simply becomes something else. What might it become? The leading idea is appealing in its tidiness. As the astrophysicist Dale Kocevski has suggested, the little red dots may only seem to disappear because their appearance changes, and what we may be watching is the formation of the cores of today's massive galaxies. The black hole at the centre of a little red dot grows up, its cocoon disperses, and the surrounding galaxy assembles around it. Over time, it stops being a strange red dot and becomes the central black hole of an ordinary mature galaxy. This idea fits a fact we met long ago. Nearly every large galaxy in the present-day universe, including our own Milky Way, holds a supermassive black hole at its centre. Those black holes had to come from somewhere, and they had to grow early. The little red dots may be those very black holes caught in their dramatic youth before their host galaxies grew up around them. What looks like a disappearance is really a graduation. The dot becomes a galactic heart. The timing supports this reading. The dots fade just as the universe enters the era when galaxies are assembling vigorously, building up their stars and settling into the shapes we recognize. As galaxies mature around their central black holes, the brief, gas-shrouded black hole star phase gives way to the steadier arrangement we see everywhere today. A modest central black hole within a much larger body of stars, holding to that fixed proportion. The overmassive look of the dots fades as the galaxy catches up, so the apparent vanishing is not a loss, but a transformation. The little red dots are not a dead end in cosmic history. They may be an early, visible stage in the long process that built the centres of galaxies, including the quiet giant at the heart of our own. When you look at the little red dots, you may be looking at the infancy of objects that are still here, all around us, grown up and settled into the cores of galaxies. There is something quietly moving in that idea. The strange red dots that so alarmed astronomers, that seem to threaten our picture of the universe, may turn out to be our own beginnings, the early hearts from which great galaxies, perhaps even ours, slowly grew. They did not break the story of the cosmos. They may be one of its opening chapters. Of course, much of this remains an active area of study, and it would be dishonest to pretend every question is closed. Before we return to where we began, it is worth pausing to say plainly what astronomers still do not know. It would be easy, having followed this story to a satisfying answer, to tidy everything away and declare the case fully closed. But honest science does not work that way, and the little red dots are still very much a living area of research. The black hole star picture is strong and well supported, but several genuine questions remain open, and it is worth naming them plainly, calmly, without letting the uncertainty alarm us. The first open question is whether all little red dots are the same kind of object. The population is large, with hundreds of members, and they are not perfectly uniform. Some show clear signs of a feeding black hole, while others show less obvious evidence. Some are extremely compact, others a little more extended. It is possible that the name little red dots covers more than one type of object, with black hole stars as the dominant kind but not the only one. Sorting out how much variety hides within the population is ongoing work. A second open question concerns the exact structure of the cocoon. The general picture, a black hole wrapped in dense ionized gas, is well established, but the fine details, how the gas is layered, where the various spectral features arise within it, how the engine's light is reprocessed step by step, are still being worked out. Different teams have proposed somewhat different versions of the cocoon structure, and the data do not yet fully settle which is closest to the truth. There is healthy, productive debate. A third question is the matter of mass, even after the Great Correction. The electron scattering insight lowered the black hole masses by about 100-fold, easing the crisis. But pinning down the precise masses of these black holes remains difficult, precisely because the bouncing light complicates the measurement. Astronomers are still refining their methods to weigh these buried black holes accurately. The masses are far smaller than first feared, but the exact figures carry real uncertainty. A fourth question reaches back to the seeds. We do not yet know, for certain, whether the black holes in the little red dots grew from light seeds, the remnants of giant early stars, or heavy seeds formed by direct collapse, or some mix of both. The dots have made the question more answerable by lowering the masses involved, but they have not yet decided it. The origin of the first black holes remains one of the great open problems, and the dots are a clue, not yet a conclusion. And there are subtler puzzles still. Why do the dots cluster so tightly in one era of cosmic history? What exactly ends the black hole star phase, and how quickly? How do the dense cocoons form in the first place, and what determines their size and density? Each of these is an active line of inquiry, pursued by many teams using the James Webb Space Telescope and other instruments. None of this should unsettle us. This is simply what the frontier of knowledge looks like. The central answer that the little red dots are young, modest black holes wrapped in dense, glowing cocoons of gas is well-founded and has resolved the original crisis. The remaining questions are the ordinary, healthy questions of a field digesting a major discovery. They are not cracks in the answer, they are the next set of doors. And so we come, at last, back to where we started, to that first surprising sky full of tiny red points, and to the quiet wonder of what they turned out to be. We began with a simple, almost ordinary expectation. Point the most powerful telescope ever built at a patch of plain, empty-looking sky, and you expect to find faint, ordinary galaxies. That is what astronomers thought they would see when the James Webb Space Telescope first opened its golden eye, 1 million miles from Earth. Instead, the images came back speckled with tiny red points of light, small and red and almost everywhere, and the long, patient work of understanding them began. Now we can answer the question we asked at the start. What, exactly, are they? The little red dots are young, growing black holes, far more modest in mass than anyone first feared. each one wrapped in a dense, glowing cocoon of gas. The black hole feeds on that gas, and the heat of its feeding shines outward through the thick shroud, emerging softened and reddened, which is why these objects glow with their distinctive red. They are compact because the engine and its cocoon are small. They are red because of how light escapes dense gas. They are dots because all of it is packed into a single point of light. The plain name we chose at the very beginning held the deepest truth all along, and the great fear, the worry that these objects had broken our understanding of the universe, has gently dissolved. The dots seemed too massive and too bright, but that was because we were misreading their light, treating bouncing photons as fast-moving gas, and treating a black hole's glow as starlight. Read correctly, with the dense cocoon accounted for, the impossible masses shrink to reasonable ones, and the universe is revealed to be exactly as lawful as we thought. Nothing broke. We simply learned to read a subtler message. There is a deeper gift in the answer too. These strange red dots may be the early hearts of galaxies, the young black holes from which great galaxies, perhaps even our own Milky Way, slowly grew. When you look at a little red dot, you may be looking at a beginning, at the infancy of the kind of object that now anchors nearly every large galaxy in the sky. The dots did not threaten the story of the cosmos. They turned out to be one of its opening chapters, caught in the act 13 billion years ago and carried to us as faint old light. That is the part worth holding on to, here at the end of the night. The light from these objects left them when the universe was a small child, only a few 100 million years old. It travelled across nearly the entire age of the cosmos, through the slow expansion of space, stretching redder all the while, until it finally fell into a 6-metre mirror of folded gold, resting in the cold dark beyond the moon. And in that ancient, patient light, we found not a broken universe, but a new chapter in how everything we know began to take shape. So the little red dots, which arrived as one of the strangest puzzles in all of astronomy, leave us with something quieter than alarm. They leave us with the ordinary, steady wonder of a universe that is lawful and old and still full of things we're only now learning to see. Point a great telescope at an empty-looking sky, and it turns out the emptiness was never empty at all. It was scattered, all along, with tiny red beginnings,